I'll be talking for 10 minutes about Trustworthy AI in Julia and how it meets supercomputing. For those of you who have never heard about Taija, it's a small and growing ecosystem for doing various things like explainable AI, conformal prediction, which is a way to quantify predictive uncertainty. Laplace Redux is a package for Bayesian deep learning. And then we have recent joiner, joint energy models, which is an approach to hybrid modeling. This package, TaijaParallel, is one of our meta packages, and it adds support for various kinds of parallelization to certain Taija packages. The focus was on having an intuitive user interface, so to minimize the cognitive load on users, to add support for both multi-threading and multiprocessing, and to make it easy to extend the parallelization methods to new packages that might arrive and new functions. Why do we even need this? So one of the drawbacks of Trustworthy AI and all the methods that people have proposed is that they tend to increase the computational burden. So to give you some examples, in explainable AI, we might often need to generate explanations for multiple people, for multiple individuals that are affected by algorithms. Conformal prediction, one of our packages, often involves cross-validation or bootstrapping. And we also have Bayesian or quasi-Bayesian methods like deep ensembles that essentially all involve tasks that can be easily parallelized. As a motivating example, so this package was really developed to support research that we presented earlier this year at AAAI, which involved generating large benchmarks or running large benchmarks of counterfactual explanations. And I had a different talk yesterday where I presented a bit more detail on this paper here. We essentially worked on trying to find a way to generate model explanations that faithfully explain model behavior. And to test our methods rigorously, we ended up running, just in the final experiments, a total of roughly 10 million counterfactuals. And this was parallelized across many CPUs, probably more than we needed ultimately, but we used our supercomputer. And the TaijaParallel package was used as the backend. Yeah, if you want to look at the code for the paper, it has its own small package, echo.jl, which extends existing packages in our ecosystem. But to be conscious of time, just to look at what TaijaParallel actually offers. So I'm actually quite new to parallel computing. So even though Julia makes it incredibly easy for newbies like me to do these things, I thought, okay, can I minimize the cognitive load for students that are working with our packages, for example, even more? And that was really the goal here. So we really now on the user-facing side have only this one macro with parallelizer, which makes it easy to parallelize many of our functions. So here we have pretty much the main API call of our CounterfactualExplanations package, which generates for some factual samples counterfactuals in a target class for a given data set, a black box model, and a counterfactual generator. And all you need to do if you want to actually parallelize that computation is to use the simple macro, so with parallelizer, and here I've instantiated previously an MPI.Parallelizer, and then we have this begin, end block, and then just the function call. So it's really, really easy now. Under the hood, what's happening is that we have this Taija base package, which ships some common symbols for our packages. So this one adds the basic functions, like a parallelize function and an abstract type for parallelizers. This is handled in Taija base so that other meta packages and core packages can call this functionality without actually implementing the computations. TaijaParallel is then the package that adds the support, and out of the box, it adds support for multi-threading. If users want to use something like MPI for multiprocessing, then this is handled through a package extension to minimize the loading times. And I think being conscious of time, I won't go into too much detail here, but just to say that it's also very easy to extend these methods because they're dispatched on different parallelizer types. So right now we have a threads parallelizer, which then enables multi-threading, and an MPI-Parallelizer, which enables multiprocessing. So there's a lot of room for extending the scope here. And it's also possible to combine different forms of parallelization in a single function. One caveat is that the functions that can be parallelized are expected to be broadcastable. So we always expect that, such as in the case of generate counterfactual, that the arguments that go into the function can be split into different chunks, and then the operations can be run over these chunks. And yeah, just one final example on timings here. Yesterday I played with this a little bit because I haven't really run performance benchmarks on this package for a while. And now, after going through some profiling and with the simple threads parallelizer, we can generate 10,000 counterfactuals for the MNIST data set on a MacBook using multi-threading in under 2 seconds, which might not mean much to anyone who's not working in this space, but to me this was really cool. So with that, I'll open up to questions if there are any.
Any questions?
Thank you so much for the talk. That was great. I'm also kind of working in a trustworthy, fair AI space, and it's nice to finally hear a talk about it. So it's been great. Thank you. I wanted to ask if you've been kind of looking at Dagger and where that's been going, and whether you're looking at supporting Dagger with your own work.
I haven't yet, but I've heard a lot about Dagger at this conference. So I've been planning already in my mind to maybe go there. Yeah, okay. Sounds like a good idea.
Thanks.
Yes. All right. Thank you.
Thank you.
Cheers.